All right, so I'll start with question 1. Consider a signal xt. Does the Fourier transform of this signal converge? So for Fourier transform of a signal to converge, it's important that the signal has finite energy, right? And it is absolutely integrable. It's absolutely summable over minus infinity to plus infinity. This is a summation of two exponentials only in the positive side. Say this is like some 3 e to the power 2t ut, and this is some 4 e to the power 3t ut, right? And we can clearly see that since both of these are increasing exponentials, the summation is also going to be an increasing exponential, which will not have a finite area under its curve. And therefore, because xt is not absolutely summable, this signal's Fourier transform will not converge. So this kind of an explanation will need to be given. Just a yes or no would not suffice in this case. You would have to explain why the Fourier transform converges or does not converge. Okay. Next question is, for which of the following values of sigma does the Fourier transform of xt e to the power minus sigma t converge? So we clearly established that the Fourier transform of xt does not converge, right? Why? Because xt was an increasing exponential, which made xt not absolutely summable. But what if we multiplied this signal xt with a decaying exponential of the form e to the power minus sigma t to get something like xt e to the power minus sigma t? In that case, now does it become absolutely summable? Does it overall become a decaying exponential which has a finite area under it? So just to check that, what we could do is just find a multiplication of xt with e to the power minus sigma t for different values of sigma. So we are basically saying that this 3 e to the power 2t ut plus 4 e to the power 3t ut is being multiplied with e to the power minus sigma t. So sigma equal to 1, that is case 1, would simply be this. Even if you do this, you end up with e to the power t ut plus 4 e to the power 2t. Both of these are still increasing exponentials, although the rate of increase will be reduced, but they are still increasing exponentials, right? So still doesn't. Sigma equal to 2.5t. So in that case, multiplying this with e to the power minus 2.5t results in what? 3 e to the power 2 minus 2.5, so minus 0.5t ut. So first term has, of course, become a decaying exponential, but the second term, 4 e to the power 0.5t ut, this is still an increasing term, right? And as a result, the summation is still not going to be finite. So 2.5 is also still not working for us. However, 3.5 means this is 3.5. So this becomes minus 1.5t and this becomes minus 0.5t. So both of them are now decaying exponentials, and it is clear that this Fourier transform will converge. Now, this was a way of presenting Laplace transform which addresses precisely this problem, that there are certain signals, just because they are not finite or they do not converge, they are not absolutely integrable. We were not able to write Fourier transform, right? But it is still possible to write Laplace transform of those signals, given we specify the region of convergence of such signals. So we basically specify what value of sigma, for what value of sigma does its Fourier transform converge, and that is only what is called Laplace transform. The same thing could have also been done. The same answer could have also been obtained by simply finding Laplace transform of this signal, right? And there you would have written, again, there are some standard results like e to the power minus 80 ut. Its Laplace transform is 1 upon s plus a, and it's also important to specify the value of sigma, where s is a complex exponential, sigma plus j omega. So when you are saying real part of s, you are basically referring to this sigma only. So you're saying that sigma would be greater than minus a, right? These are some standard results which we can always make use of. And from this, if we look at this particular signal, we notice that its region of convergence is 3. That means basically anything greater than 3 for sigma greater than 3 would have fallen into region of convergence. Okay, so 3.5 is clearly above it. That means 3.5 is in the region of convergence, while my 1 and 2.5 were not in the region of convergence, and that is why Fourier transform does not converge for 1 and 2.5. So next part says determine the Laplace transform xs of xt, and then you sketch the locations of poles and zeros. For the first term, as we know already, we would have 3. So let me call xs as the Laplace transform of xt. So you would have 3 upon s minus 2 plus 4 times, because Laplace transform of e to the power at ut is 1 upon s minus a, right? So this becomes s minus 3. When you solve it and take out 7 common, you should end up with this kind of an expression. Okay, so this is how you end up with xs. And now because you have this ut multiplied, this gives you an idea of which direction should the ROC be towards. So let us quickly find the zeros and poles. So you have a 0 at 17 by 7, and you have 2 poles at 2 and 3, right? So now I'm going to sketch the ROC. So this is the S plane we are looking at. This is the sigma axis, this is the j omega axis, and ROC is drawn in terms of sigma. That means these are vertical strips parallel to the j omega axis. So let us first point out the poles. So we have a pole at 2, we mark it with a cross, and there's another one at 3. Okay, we know that poles cannot be a part of ROC, like poles cannot fall in the ROC, right? 17 upon 7, this is some 2 point something. That means this lies between 2 and 3. So this is where the 0 lies, somewhere in between. 0 is shown with a circle and poles are shown with crosses. Now, what are the options for ROCs? ROC has to be vertical strips parallel to the j omega axis, and it cannot contain any pole, right? That means it could either have been something like this. The dotted line shows that this particular value is not included. Okay, if it was a straight line, that means it is included. Like how you draw in number line, how you show it like this, right? If you leave the circle, that means this value is not included. The same way for showing it in 2 dimension, if I'm showing it with a dotted line, that means this value is not included. So this was one option. The other option was this. Right? Because this is a right-sided signal. Right-sided signal means because this signal is multiplied with ut, means it's a right-handed signal for t greater than 0. That is what this is defined for, right? That is why the ROC would be right-sided. Okay. So this is how the ROC of this function looks like, and that is where we need to still complete this Laplace transform, because leaving it just at an equation is not enough. You also need to write the ROC. That means you have to write that real part of S greater than 3, right? Greater than 3. This is the Laplace transform. Please always know that you cannot leave Laplace transform just with the expression of S. You also always have to write the ROC. Because you could have had the same expression for 2 different types of signals just because the ROC was different. So it's very important that to uniquely map one Laplace transform with one signal, you need to write the ROC also. That is only how it is going to be unique. we move on to next question. Question 2 says that if xt is an even time function such that xt is x of minus t, show that this requires that the Laplace transform is also even, right? xs is equal to x of minus s. So how do we go about this? We will simply write the expression of Laplace transform. xs can be written as, this is how Laplace transform is defined, right? Now, we have another function, let x of minus t, let me call this as x1t, right? And let the Laplace transform of x1t be x1s. So let me write x1s. How would x1s look like? This would be this. Let me have an intermediate, like some change in variable. So let me say let minus t be equal to some new variable t dash, right? So in that case, I would have minus dt equal to dt dash. That means dt is minus dt dash. I'll just make some substitutions. And in terms of t dash, which is my new dummy variable, I could say this is x of t dash e to the power minus s. T is minus t dash, right? So it becomes plus dt dash. There would be a minus here, but again I can flip the limits and still between minus infinity and plus infinity. So this in terms of x s sounds as if this is nothing but x of minus s. That means just instead of s you have a minus s. Okay, but we also know that xt given, that xt is same as x minus t. That means their corresponding Laplace transform also need to be identical. So we just found that x minus t's Laplace transform is x of minus s. That means since the signals are equal, their Laplace transforms also need to be equal. Hence we have shown that if the signal is even, their Laplace transform xs is also same as x of minus s. Okay, this was for part A. And for part B, we need to show that the same thing. If it's an odd function, we need to show that x of s comes out to be minus x of minus s. So we do the same thing again. Again, doing the same kind of substitution, t dash, this becomes, right? And this is nothing but minus s of minus s. So we can say that x1s is equal to xs, and since it is given that xt is same as minus x minus t, because xt was given as an odd function, we can say that xs is same as minus s of minus s. These are basically two findings which would later help us identify signals just by looking at their ROCs. Okay, so what this basically tells us, that if your signal is even, then the respective Laplace transform functions, at least the function in S, are also even. And if the signal is odd, then your Laplace function is also odd. Remember that then it's not mentioning anything about ROC, and just by looking at ROC, do not jump at the conclusion that something is odd or even. You will always have to write the function, and that is what the next question demands to do. Okay, so part C basically says that we've got 4 plots here, and looking at these plots, we have to determine which of these corresponds to an even function. Let us look at the first part, right? First part, how can I write this? You notice that there are 2 poles, one at -1, one at 1, and there is a 0 at 0, right? That means if I had to write this function xs, this would be of the form, let there be some constant k. We don't know what that constant is. We'll just leave it as k. But if I had to write the expression, it would have a 0 at 0, and it should have one pole at -1 and one pole at 1. So it would be of some form like this. This corresponding to the pole at -1, this corresponding to the pole at 1. This would be the form of XS for part 1. Now let us see what would x of minus s look like. Just plug in minus s everywhere. Okay. So this tells us that this was x of s, but x of minus s is not equal to xs, right? Instead, we have found that x of minus s came out to be minus xs. This cannot be even. Then we go to the next part, part 2. Let us try to write part 2 also. Part 2 would be something of the form k times, there is a pole at 0, okay, one pole at 0, so denominator mein s, and two zeros, one at 1 and one at -1. Let us see if so. This also cannot be the ROC of an even function. We move on to part 3. Part 3, xs would be something of the form. We have two zeros at j and minus j, right? That means we will have something like k times s plus j, s minus j, and two poles, again it's 1 and -1. Okay, now let us try to find x of minus s. Which is nothing but x of s, right? So for this particular case, we have shown that x of minus s actually comes out to be x of s. That means this must be corresponding to an even function. For part 4, you have 1 0. That means xs is of the form s minus 1. And there is only one pole, that is again, this is not equal to xs. So this is also, this cannot be even. This cannot be the ROC of a function that is even. Okay, so the only candidate we have is part 3. So what the question asks is that for those that could be even, right, indicate the required ROC. So the part 3 is the winner here, and let us sketch the ROC. Another thing that we should understand at this point is that when we have a signal which is even or odd, right, that means there is a, say in this case, we are looking at particularly even functions. That means we are looking at the condition that x of minus t is equal to xt. That means we are looking at two-sided signals. Meaning, if the signal was one-sided, just for example, if the signal was a one-sided signal like this, say this is some signal xt, right? Only one-sided, it is not two-sided. There is no way for it to be even or odd. That means the moment we start talking about such signals, the signal has to be, it doesn't have any other option, it has to be a two-sided signal. That means it has to have a term of ut, it also has to have a term of minus ut somewhere in it. That's the only way for it to become a two-sided signal. And the moment you have a two-sided signal, it becomes easier for us to understand how the ROC should look like, because in this particular case, obviously you cannot have, we know that ROC cannot contain the poles. That means the edges of the ROC have to be these two. right? And then the only option we are left with to include both the cases, that means left-handed signal also, right-handed signal also, is to have ROC here. Okay, because this would have been what? This would have been an overlap of this one term, which would have been left-sided, right? Means a term which had a pole at 1, but which was a left-sided signal, something with u of minus t. And then you would have another term whose pole is at -1 and it's a right-sided signal. This would have been the ROC for that particular term. And then you would say that overall, because overall it has to be an overlap of these two signals, the common area would have come out to be this, the hatched area. That is the only common area between these two ROCs. Okay, so for a signal to be odd or for a signal to be even, it's important that the signal is two-sided. So when anybody asks you to sketch the ROC, you've got to take that also into account. So the answer for this case, this is the ROC between -1 and +1. Okay. The next part says, determine which, if any, of the pole zero plots could correspond to an odd function. For those that could indicate the required ROC. So if we look at part C1, the first one that we solved, here you could say that this was the condition that we showed in the previous part to be true for an odd signal. We couldn't show that for any other signal, right? However, this is one case. These, because there is only one pole, and here also there is only one pole, we do not have any condition of this being a two-sided signal. So these two are again disqualified. The only thing we are left with for, remember that now we are looking at odd function, right? So this is the only thing we are left at. And in such a case, also the ROC for it to be a two-sided signal would have to be. Moving to question 3, we have what is mentioned as a causal LTI system. Okay. Now there are some subtle terms in the questions always. We need to read into them very carefully because they are hints for us to understand how to solve this question. So the first part, what this says is that there is an LTI system. It's not just LTI, it's also a causal LTI. That means it's right-sided. Okay, and they are related by this kind of a block diagram. So this whole thing is nothing but a representation of some signal like this. If I was writing it in time domain, I would have written like this: takes input xt, gives output yt. If I was writing in complex frequency domain, this is how we would write. First part says, determine a differential equation relating yt and xt. Okay, so the first stage here to understand is that these blocks which are drawn, what does this mean? You have a block 1 by s. What does it mean? This 1 by s is the transfer function of the block, right? That means, now what is 1 by s the transfer function of? Let us see. Just to have some ground rules set. So say I have a signal xt whose Laplace transform is xs, right? So if I now have a function d by dt of xt, we know that its Laplace transform would be s xs. That means if I had a system that does differentiation, and if I asked you to find the transfer function of such a system, what would that transfer function come out to be? So this is the output and this is the input. So you would have said, this is the output, this is the input. The transfer function of such a system is s. That means if I was to have s instead of 1 by s, you would have said that whatever is the input, the output is the derivative, right? If I just reverse it, then do you see that if I was integrating, if this was an integration, right? That means d by dt of xt is the input and xt is the output. For such a system, what would you have got as hs? 1 by s would have been the transfer function. This tells us, this understanding tells us that this function 1 by s is nothing but an integrator. Okay, so you might be confused to see that there are terms of t also here and then there are terms of s also here. What does that mean? This is just to show what this particular function does. Okay, so the moment you see a 1 by s, it is nothing but an integrator. Okay. What this also tells us that if we define some intermediate function, so let me have an intermediate function, say w1t, there is an output w2t, and let this be some w3t, right? Because that makes the whole solution a little bit easier. If that was something I could write in terms of some intermediate signals, which I'm just naming here. Remember our ultimate task, we need to find a relationship between yt and xt, right? But there's a lot of feedback, there's a lot of recursive kind of a nature here, which is why we need intermediate signals to help us solve this question correctly. Now, knowing that this is nothing but an integrator, can I say that w1t is d by dt of w2t? Would it also be correct to say that w2t is nothing but derivative of w3t? And here you already have a w2t. That means this is same as saying d2 by dt square of w3t. Now, having understood this, let us first write the relationship in this direction, means between these terms, between xt and say one of these w1, w2, w3. And once we've done that, we'll write the relationship between yt and these terms, and then we'll get rid of those intermediate terms. Okay, so if this is what I had to write, okay, let me call this as summer 1. Okay. So at summer 1, can I say that w1t, this is equal to this plus this, isn't it? That means xt plus whatever is the output of this summer. What is the output of this summer? Minus 2 times w2t minus 1 times w3t. And good for me that I already know the relationship between w2, w3 in terms of one common term. I know that w1t is nothing but this xt minus 2 w2t. I know that w2t is this in terms of w3t minus w3t. Great. Now that I know this and I know that this is an LTI system, I will bring in Laplace transform. Find Laplace transform on both sides, because it's easier to represent things in terms of a polynomial than to carry differential equations and then solve it, right? So I'm just going to find Laplace transform on both sides. That is going to give me, I should write that, let w3s be the Laplace transform of wt. This is capital W, this is lowercase w. So in that case, if I was finding Laplace transform on both sides, I get this is one equation. I've got w3 in terms of xs. Now things are simpler because I need to do the same thing here between yt and these w terms. Okay, so now if I'm focusing on this summer number 2, let me call it, can I say y t is equal to this plus this. That means output of this summer, which is nothing but minus 1 times W2t minus 6 times W3t. Again, I know certain relationships between them. I'll just rewrite them. And this becomes, and we could say that ys, which is the Laplace transform of yt, now you've got two expressions describing W3. Let me just equate these two. So I've got xs upon s square plus 2s plus 1 is equal to ys upon s square minus s minus 6. Let me cross multiply. That means s square xs minus s xs minus 6 xs is equal to s square by s plus 2s plus ys. Now, looking at both LHS and RHS, we can, if I try to find inverse Laplace transform on both sides, I can clearly see that this means this would have been a Laplace transform of this term, the first term, right? Second term would have been this. Third term would have been this. RHS, this would have been d2 dt square yt plus 2 d by dt of yt plus yt. This is your answer. This is what was asked, to find relationship, differential equation relationship between xt and yt. So we brought in intermediate variables and then used Laplace transform to simplify the expression. Then we eliminated the intermediate variables. We go to the last question. In the last question, it is given that we have an LTI system. We are also given what is the Laplace transform of the input. Another additional information which is casually slipped in here is that xt equal to 0 for t greater than 0. That means xt is a left-handed signal, left-sided signal, because its value is all 0 for positive t. That means it is a left-sided signal. And we also know what is the expression. So we have a system defined by some ht. It's an LTI system. In terms of transfer function, it is defined as some hs. Okay. So the yt is also given and some information about signal is given. First part says determine hs and its region of convergence. Right? So very simply, xs is already given to us. We already know that if these things are known, we know that hs is simply ys upon xs by using the convolution property of Laplace transform, which is the same thing that holds for Fourier transform as well. Right? This we already know. So xs is already given, yt is given. So let us quickly find ys. Ys would come out to be 2 by 3 s minus 2 for this term plus 1 by 3 s plus 1 for this term. You notice that this term is left-sided while this term is right-sided. You should get s upon okay. So this is the ROC for the first term because it was a left-sided signal, right? And the ROC for the second term should be everything to the right of 1. So the only area of overlap that we see here is this That is the only common region of convergence, and that is why we would have to say here that if this is the expression of ys, the ROC, the real part of S, is everything between -1 and 2. Okay, everything between -1 and 2. This is what is ys. We are still not done because we had to find hs. hs is ys upon xs. Okay, so there are some other information here which will help us determine what should be the ROC, but let us first deal with hs, right? So hs, since it is known as ys upon xs, ys is this s upon s minus 2, s plus 1 divided by xs. What was xs? S plus 2 upon s minus 1. So this and this gets cancelled, and you would end up with s upon s plus 1 into s plus 2. We have not yet said anything about the region of convergence. So, okay, so here is something where we will need to look at what was given very carefully. It said that xt is a left-sided signal, right? You know that the moment you have a system that takes some signal, say xs, gives a signal ys, you know that the ROC of ys has to be what? It has to be an intersection or the common area of these two, right? Because these two are going to get multiplied. What was found to be the common area? This hatched area, right? I'm going to remove all the other things. The ROC of ys has to be an overlap between ROC of xs and ROC of hs. What we know about xs is that it is a left-sided signal having a pole at +2, right? That means the ROC of xs had to be this. I'm talking about ROC of xs. The overlap between these two has come out to be as this hatched area, right? So the only way in which the overlap or the intersection between this yellow part and something would come out to be this hatched area is if the other area was this, right? So that is what has to be the ROC of hs, because the overlap, which is the ROC of ys, the output, is this hatched area. This is what tells us that the ROC is real part greater than -1. Now that we have hs, the next part asks us to determine ht. So very simple. We have the function, just need to find its inverse Laplace transform, ht, which is the impulse response. Now you use partial fractions, break this up. You should get something like some term like this. And knowing the ROC, now you can make a informed decision about what should be the function. So the first part, what does this say? That you have some function whose ROC is like this, right? So it's a right-sided signal, clearly. It is not a two-sided signal. Obviously, it's a right-sided signal. So you already know that in that case, 2 remains as it is. So this becomes e to the power minus 2t ut minus 1 e to the power minus t ut. The only thing that this ROC helped us determine was whether or not we had to write e to the power minus t ut, or did we have to write minus e to the power minus 2t u of minus t, because both give us the same expression, right? But the ROCs are different depending on the direction. So we have t. So both these parts are done. Now the third part says, using the system function hs that we just found, determine the output yt if input is this, okay, for all t. Now you can see that this is an exponential function, and this is where again look at what it says. It's an LTI system, right? You already know that a complex exponential is an eigenfunction of an LTI system. What is the meaning of eigenfunction? Eigenfunction of a system means if you gave that function as the input, the output is the same function just multiplied with some scalar, right? So there is no change in the function except that it is multiplied with a scalar. That means it could have been scaled up, scaled down. This could have been a negative number. That means there could have been a reflection also, but the function remains as it is. There's just multiplication with a scalar. And we know that for an LTI system, we know that that is nothing but Hs, right? That constant comes out to be Hs. If the input is e to the power st, we know that the output is simply some Hs times e to the power st. Because this is the case, we say that e to the power st, a complex exponential, is an eigenfunction of an LTI system. Means e to the power st comes out unscathed, just multiplied with a constant if you pass it through an LTI system. Now, in this question, it is given that the signal which is being given in as the input is e to the power 3t, right? That means s is equal to 3. S is a complex variable of the form sigma plus j omega, but here s is equal to 3, right? So in such a case, because you know already that e to the power st is an eigenfunction, you can simply say that yt for such a case should be simply h3 e to the power 3t. Hs means Hs at s equal to 3. That is what you have plugged in here, right? And Hs you already know. This is Hs. Just plug in H3 means s equal to 3. So you've got 3 upon that means 3 upon 20 e to the power 3t. This is the output.